product where that's wedged, and then you'll have another product here where that's dashed. Right,
And
both.
what's the reason again?
Say again.
What's the reason?
So that, do you agree that this is a chiral center?
Oh yeah.
Yeah.
Yeah. So remember we talked about how to induce chirality, and in order for you to do that, you need some type of bias, right? You either need a pre-existing chiral center or you need like a catalyst that's chiral, and you have neither in this case. So you're going to get a racemic mixture. Both of those products will be formed in the same amount. Did you just throw your pen? Like, what the?
That was my pen.
Oh, okay. All right. I'm just making sure. Was that you, Sage, that was asking that?
Yes, that answers the question.
Okay. All right, cool. All right. Now, let's go to another concept. And I got to erase all this stuff. So, and don't panic, because did y'all see the videos I put on YouTube?
I just saw one.
It should have been 3, because I had to chop it up in 3 pieces.
When I watched it, it was 5.
Was it 5?
It could have just been
5
me.
pieces?
Yeah.
Yeah, it was 5 pieces. My bad. Sorry about that. I was trying to be, trying not to spook you. But yeah, I did have to chop it up in 5 pieces, because the video itself is like 55 minutes long or something like that. So I had to chop it. And then I chopped the end off too, because that was just us rambling, talking about random stuff. But I had to chop it up so that you can meet the time constraint, because you can only post like up to 15 minutes or so. So I will have this chopped up and recorded and all that stuff. But now we need to talk about another
Wait,
concept.
Dr. Russell, can you scroll up a little bit?
Scroll up to here?
Yeah. Thank you.
Mm-hmm. Can I erase the third example? Where we talked about stereo specificity. Can I erase that?
Yes.
All right. So we'll erase that because I need some room for the top example. All right. So what do you notice about the example number 2?
We got the product.
Got
we
the
got to
product,
make the starting part.
but no start material. So just like we did with those grignards, we're gonna have to work backwards, right?
Mm-hmm.
Anybody remember that term? Oh Lord, never mind. It's called retrosynthesis. Is that right?
Yeah.
Where you start at the product and work backwards to the start materials.
Mm-hmm.
All right. I'm just making sure that I've been teaching something this year, a little something. All right. So with a 4+2, right? You know that this is the product of a 4+2 because it's a 6-member cyclohexene ring, and so to work backwards is actually easier than going forward. My strategy that I'm going to give you is to always start at the double bond. So start right here. All right. So let's see if we can figure this out. So if I take that double bond and let's say I shift it this way, what does that mean?
The double bond is going over there.
So I'm going to put the double bond right here. Is that right?
Mm-hmm.
Yes.
Yes.
And if I do that, this carbon right here, I got to do something about that carbon because otherwise it's going to have too many bonds. So I'm going to take this bond and I'm going to shift it to here. Right? What does that mean?
It's going to be a double bond.
So I'm going to have a double bond right here. Is that right?
Mm-hmm.
And then and that's going to cause a problem for this carbon. So I'm going to take this bond and I'm going to shift it to here. Uh-oh, not like that. Like that. Right? So what I've effectively done, let me see if I can get this to work if I use a white highlighter. I've broken this bond. Really? That ain't working. Let me see if I can use a white pencil. Yeah, so I broke that bond. Is that right?
Yeah.
And I also broke this bond. Yes? Isn't that what the arrows indicate?
Yeah.
Mm-hmm.
Yes.
Right, so this arrow right here.
On the bottom, get a double bond, right?
Say that again.
I said the arrow that's pointing to the bond at the bottom, it turns to a double bond, right?
Oh, hold on. Let me get my highlighter together. This one right here.
Yeah.
Yeah, it's gonna put a double bond right here.
Okay.
Yeah. Sorry for my little dots. Don't trip about that. Right. So this bond is breaking, and so is this bond. Is that right?
Mm-hmm.
So on the other side of the arrow, the start material side, right, I'm going to have this. Do you agree?
Yes.
Plus what? All of this.
Double bond with the circle,
I
the
mean,
oxygen.
oxygen. Yeah, come on now. We got to talk some scientific jargon now. All right. Is that right? It's ugly, but it's right. Put my circles back in. Yes or no?
Mm-hmm.
Yes.
And if I erase all this other crap over here, you'll see that, right? And if I want to go forward, it would be here, here, and here. Yes or no?
Yes.
Yeah.
Mhm. So the retrosynthesis is actually easier than the forward way, because if you just start at the double bond that you have, you can work backwards. So let's do another one. And then we're going to work through some examples down further down in the handout. All right, let me erase this.
Dr. Russell, I had a question.
Go ahead.
Is there any way to make that this carbon ring without it being a 4-2 situation?
Any way to make this?
Yeah, without it being the 4-2.
Oh yeah, there's a lot of other synthetic pathways that you can take. I can give you one right off the top of my head. Right, if I started with something like this, put my oxygen in. Man, what if I started with this? I could do an elimination. I mean, if I just want to put an alkene there, I can do an elimination, right? On something like this, where I just treat it with a strong base and do an E2 elimination. So there are multiple ways. That's one the thing about organic, is that there are always more than there's always more than one way to get to a specific product. Right. That's why you always have a toolbox full of different reactions that you can use to do the same thing. But in this case, since we're discussing the 4+2 cycloaddition, then that's why we know that the start materials have to come from a 4+2.
Oh, okay. Okay.
Yeah. All right. Let's do the bottom reaction. Where are you gonna start here?
The double bond.
Start at the double bond. Right? And I'm gonna do this. Is that right? Don't touch these bonds right here. And I'll show you why when we get to the start material. Those bonds have no bearing on the reaction. As a matter of fact, let's number this. 1, 2, 3, 4, 5, 6. You following? So what bonds are we breaking? Are we gonna break the bond between 1 and 6?
Yeah, 1 and 6 and 4 and 5.
4 and 5 and 1 and 6. That's exactly right. So I'm going to do this, and then I'm going to need to zoom in so I can get into that little crevice. I'm going to take this and put it here. Is that right?
Yep.
And I'm going to take this and put it here. Dang it. Here. Yes or no? Right. Keep in mind, I'm not touching these sigma bonds right here. So what would I get from that?
You get your diene.
Let's pick this part out first. What is this part going to look like?
Wouldn't the double bond be between 6 and 5?
Yes. So you got a double bond between 6 and 5. You're right about that. I'll even keep them numbered. That's 5. That's 6. Should it be trans or cis?
This.
Trans.
It should be trans, right?
Okay.
You see how the OH group is on a wedge and the bromine is on a dash?
Mm-hmm.
Yeah, so that should be trans. So we can, and it doesn't matter which trans isomer you draw, right? Whether you put the bromine on this side and the OH on this side, it doesn't matter. But we know that it has to be trans because what's the term again about the reaction? It's always what?
Stereospecific.
Stereospecific. Exactly. All right. So that's my dienophile. What does my diene look like?
I'm gonna put the oxygen in.
So oxygen didn't go anywhere, right? And then it's still connected to 1 and 4. Is that right?
Mm-hmm.
So then when you just do the double bonds at 1 and 2.
Mm-hmm. Yeah, that's exactly right. So this is 1, 2, 3, 4, right? So the dienophile is actually a ring. Can you see that?
So the one with oxygen attached, that is the dienophile.
Yeah. No. Which
Oh.
oxygen now? The OH or just the oxygen by itself?
Just the oxygen by itself.
Yeah. No, this is my diene.
Oh.
Right. Di means 2, right?
Right.
Ene equals alkene.
Alkene.
Right. And you can see that there are 2 alkenes right here, one here, and it's conjugate.
Okay.
Yes, no.
Yeah.
Yeah.
So
Yes.
the product over here, can you see how? Let me do this. I'm gonna erase all of this. Can you see how in the product it looks kind of like 2 rings fused together?
Yep.
Right. The way that you can tell that either your dienophile or your diene is a ring is if you have a bridge. You see this oxygen right here? That's called what we call a bridgehead.